taking a 400-pound engine from the back, taking away the two bladed props. We installed, oh, it paused here for me. Did it pause? Here? 18G crash-worthy structure with the 16 battery modules for 800-volt system. We put in the new motor mount with the for the MRAX electric motor. Equipped it with 3 bladed props, front and rear. The only difference now is the rear is electrically actuated because we lost our hydraulic system in the back of the aircraft. Next, an 800-volt DC to AC inverter, along with high voltage electric cabling. And finally, a liquid cooling system for the motor and in the back end of the aircraft. So prior to doing any of that on aircraft, we took advantage of one of the labs over on Montreal Road here in Ottawa and put all of these systems into one of our test cells so we could learn as much as possible about the new systems in a very controlled environment before we got into ground and flight test in the actual aircraft. The only major limitation we had in that test cell is we couldn't operate a propeller in there, so we had to use a dyno. So this is what it really looked like. And we kept everything as representative as possible in that lab. All the high voltage cables were cut to the same length. We had a representative cooling system. We had aircraft batteries, the actual batteries inside their containment, inside a battery box that simulated the approximate size and volume of air that would be around them inside the aircraft. We took the prototype aircraft cockpit display, which you'll see later, and we used it in the test cell. And it was instrumental in developing the actual display that we ended up with in the aircraft. There were a few limitations. We can't test everything, obviously, in a test cell. For instance, the dyno couldn't replicate propeller dynamic or transient characteristics for feathering. But the test cell was instrumental for thermal dynamics and performance validations and predictions. Data from the test cell was fed into a model, and that provided the flight crew with fairly accurate estimates and predictions of the thermal characteristics of multiple systems, as well as power and performance for us to get off the runway. The go-around was deemed the most critical part of our flight profile, because initially all we wanted to do was get up, fly one circuit, and land, but have the capability to go around. The reason the go-around was deemed the most critical was at that point in the flight profile, the temperatures of the battery, the motor, and the motor controller were all elevated. So in the test cell, we were able to perform the planned flight test profile to determine which parameters would be the most critical and if any limits would be exceeded. It soon became obvious to us that the batteries themselves and the motor controller would be the critical components and needed the most attention. Overheated batteries risk damage or, in worst case, thermal runaway. Semiconductors and controllers fail rapidly when overheated. An overheated motor risks permanent degradation, coil insulation breakdown, or irreversible permanent magnet weakening. The placement of the probes, the temperature probes within the battery modules, is a significant issue. And for us, we were not fortunate. We had modules that are already pre-packaged with probes in them, and they were not always in the most optimal locations. Probes near the high voltage connections became the hottest, and they were not always representative of what the actual thermal characteristics of the entire module were. In the future, we prefer to have individual cells in the core of the battery instrument so that we could have a better indication of what the condition of the temperature in the middle of the battery was. Our first lesson learned was that you can mitigate and resolve many of the electric propulsion system risks prior to first flight, and you're never going to waste time in ground test and in the test cell. So it was funny that we named this project Heat because we found that it all became about the heat. Based on the lessons from the test cell, thermal management became a key consideration for us during flight test. We set a fairly conservative max temperature limit for the batteries of 50 degrees Celsius. This is nowhere near these batteries would enter a thermal runaway condition, but based on the longevity and the health of those batteries. Now, having been adopted from the automotive industry, the batteries were not designed for long durations of high power. Nobody takes their Tesla from the stoplight, puts the pedal to the metal, and keeps going for 10 minutes with the pedal fully down. So these batteries were not optimized for the way we would do it. With maximum power set for takeoff in our first stage of climb, we would increase temperature about a degree every 10 seconds in our battery modules. So this closely matched what we had predicted from the test cell results. Hence, we only had about 5 minutes at max power prior to hitting our limit. But like I mentioned, most of the highest temperature was at the connectors. So when we reduced power or removed it completely from the back motor, the temperatures reduced fairly rapidly, and we were able to continue on with more testing. Another benefit of testing in the test cell that we could accurately determine the efficiency of the motor based on temperature. We determined the motor efficiency dropped off as it got hotter, as you can see in the graph in your bottom right. Resistance in the coils goes up, and magnetic flux in the permanent magnets go down. Overall, power available is now a function of motor temperature, or its efficiency, and battery state, voltage versus current, not the outside air temperature and density altitude that we've been accustomed to with our air-breathing engines. As mentioned earlier, is operating. Actually, this one has sound, so it's impressive. As mentioned earlier, we set conservative limits to avoid thermal runaway. After watching this video, you're going to understand why. This is one cell burning on purpose. We have 192 of these cells in our aircraft. For certification, I might have to turn that down. For certification, you're either going to have to prove that your batteries will never do this, they'll never go into thermal runaway, or you're going to have to prove that you can contain it. Each of our modules are contained within titanium enclosures, which we are calling cake pans, which you can see in this model and you'll see in the aircraft later. Each enclosure is vented externally from the aircraft. So our strategy was avoid this if at all possible, but if not, contain it and vent it overboard so that we can get back on the ground safely. So again, we benefited from other labs, and in order to determine if thermal runaway could be contained, we set up a test rig with actual battery modules inside their containment enclosures. Then caused one module to go into thermal runaway with witness modules sitting one beside and one above in the proximity that they would be in the back of the aircraft for worst case locations. In another lab, not in this lab. Yeah. No, over on Montreal Road. So we are fortunate that other labs within RC have already have these capabilities to test batteries, specifically for electric vehicles, which they've been doing for about a decade. We made great use of the aptly named Battery Abuse Lab, which we could do these types of things in to run batteries to destruction. During our first containment test, the containment system buckled under the heat. We had massive fire, noxious gases, and it was a complete failure. In the second test, we were almost successful. It appeared to be containing until one of the insulation on one of the high voltage cables inside one of the modules melted away, allowing the high voltage cable to contact the casing. In essence, we created an 800-volt arc welder, welded a hole through the top of the casing, allowing the gases and flames to exit. Finally, on our third attempt, about a year after our first bonfire, we were fully successful. The system contained the runaway for over 20 minutes, venting all the gases and fumes outside of the containment system. So this gave us the confidence we needed to strap into the cockpit with these modules sitting right behind us and making sure that we didn't have to worry about getting barbecued. So our lessons here are these battery risks are new and they can look quite scary, but they can be mitigated. And since we were operating these batteries, like I mentioned, in a way they weren't designed for, because the particular batteries we have came from automotive, we wanted to do some further testing. So we subjected a module, a full module, one of our 16 modules, to 100 flight representative cycles in the lab. The module showed no degradation after 100 cycles, and in fact, the discharge capacity increased slightly after being broken in. So finally, moving on to ground test, actually getting into the aircraft, we started seeing different things that we hadn't seen in the lab. We started having intermittent failures of our cockpit display. Through some extensive troubleshooting, it was determined that we had an EMI problem coming from our 800 volt inverter. It's a very noisy system, and on our CAN bus, it was driving noise, causing failures of our display. One of our electrical engineers recommended a choke, so we grabbed what we have. You see in this one, we jerry-rigged the choke that was already on a circuit board into the back of the aircraft, and problem solved. Errors went to zero, and the display worked great. So later in the ground test program, we had a similar issue with our electrical prop governing system. I mentioned we have electrical prop now, and the prop didn't always govern, and we saw quite a few issues. So we hooked up some scopes, we looked into it, and we immediately jumped to the conclusion, we're flying a big electromagnet, we have EMI problems again. So we chased that down a rabbit hole for a couple of weeks to no avail, only to find out it was actually just a rigging problem on the prop itself, had nothing to do with EMI. So again, we learn lessons as we go. As things happen, you start to expect. You got an electromagnet, you got all these problems with EMI, you see something similar, you get dragged into it. So we literally and figuratively got scope locked on what we were doing. I'm now going to pass over to Ray to talk about the more fun stuff as we got into more ground and flight test.
Thanks, Pete. So yeah, I'll talk a little bit about the controls, the displays, some of the mitigations we had to put in place because we were using non-flight rated hardware. So the display that you see up here that we're using primarily for our engine indications for the rear is actually an industrial display. It's probably more at home in a machine shop or on a tractor than it is in an aircraft, but it was what was available and we could program it. So the way we set it up, the top half of the display is typical of what you would see on most engine indications. So all the information we need to be able to manage and control the rear propulsion system. The center row, we have some annunciators to idiot lights, essentially to indicate that we've got a fault with the system, that we need to react to something. And then the bottom half is set up as status or synoptic pages so that we can troubleshoot a little bit deeper. Not really required to deal with in flight, but we're doing an awful lot of ground testing and an awful lot of troubleshooting and data gathering in flight. And so we set up these synoptic pages. There's actually 3 of them we can scroll through and get different temperatures and voltages and things like that. So across the top, kind of typical what you'd see, RPM, we've got a torque setting. We've got the hottest temperature of the battery up at the very top right. And then in the bottom, you can see a tic-tac-toe board with a bunch of numbers. So the one at the top that I react to is the hottest temperature out of all the batteries. But if we wanted to dig down and troubleshoot, we could look in that tic-tac-toe board and figure out which of those batteries is hot. Are they all hot? In which case I've been using the system hard and I maybe just need to reduce the power. Or do I have one battery that's much hotter than all the rest, indicating maybe I've got a faulty battery and maybe a more serious problem. We also had to mitigate the fact that this isn't to design assurance levels. It could fail, it could freeze. And so we had some backup indications beneath it, these lights down here that provide us secondary status indications, so that if we lost the primary display, we still had a basic indication of what's going on in the back end. Can I keep it running? Do I need to shut it down? You'll also see there's one marked HV ISO, high voltage isolation. There's a separate system that's monitoring the insulation on the 800 volts and can detect if we've got an insulation breakdown. And so a warning that maybe one of the lines is chafed or shorted, or we have some kind of electrical problem at the back. But then we can then land, notify maintenance. They can come out in the special arc flash chute and protect it. We also had a couple of non-software overrides. So down at the bottom, you can see some additional switches. So we have an emergency stop, which actually our industrial guys hate because it's not technically an emergency stop switch, but it does the function we need it to. It's a way to remove power from the system when we don't want it. So for example, we get a software fault that causes the rear motor to spin in reverse, which is possible. It's an automotive system. It's set up for doing forward, reverse, braking, regeneration. We tested those in the lab to make sure they wouldn't pop up. But again, it's not Dell certified. It's not aviation level. So we wanted to have a way that we could positively remove power that was independent of software. And so that's what the emergency stop switch was for, was to kill it when it was doing something we didn't want. On the opposite side, we've got a controller override. The system, again, designed for automotive, will shut itself down to protect itself. We don't want that in certain phases of flight. And so we have a manual override that we will sacrifice the back end so that it'll continue to produce power and get me back home. And so we kind of had those two overrides to deal with that non-certified level of software that you wouldn't normally see. Yep. Okay, wasn't sure if I was going to be too loud standing in front of it. So, all right, I will stay on this side. So yeah, lessons learned. Early involvement of the flight test crew in the test cell was critical. So we, as Pete mentioned, we had a lot of inputs into how this was designed. Early on, it was set up for doing lab testing. And the size of fonts that works well in a lab when you're sitting up right close to the screen don't work in a cockpit when it's busy and vibrating. We also needed to assure that we were going to be able to safely fly the aircraft if we did have a problem. So we did a number of things to increase our chances. The rear propulsion system doesn't operate without 28 volts from the aircraft. All the computers run off ship set battery and the alternator on the front. Well, we'd gotten rid of half the electrical system on the aircraft. There's normally an alternator on the rear. We'd gotten rid of that. And so we actually increased the size of the alternator on the front motor, and we upgraded to a larger ship set battery, far more capable, just to assure that we would have that electrical power to keep the rear propulsion system running. Our front propeller looked like somebody had been mowing hay with it. We're a government organization. We buy from the lowest bidder. And so that front propeller was fairly worn. And so we opted for the newer 3-bladed propeller to restore some of that thrust loss that we figured we had lost from that worn propeller. We also incorporated a STC for the landing gear doors. On a normal 337, those doors open, create a lot of drag. And so we replaced that with an STC system that reduces the gear retraction time and cuts down a lot of the drag. We also did a lot of simulation and modeling. So they had simulated what kind of thrust we'd be able to get from that rear propeller, what kind of performance we'd be able to get, what part of the flight envelope were we vulnerable, where if we couldn't feather the rear propeller, would we still be able to climb or would we descend? And we used all those simulations to build some test numbers and be able to get a good idea of what we're going to be able to do with the aircraft. We then went out and did a whole bunch of ground testing to try and validate those models. So we gathered data before we modified the aircraft, checked the model, make sure the model matched what we predicted. We went through, modified it, and then did a bunch of other ground testing to confirm that it was actually doing what we expected. So by the time we got to the flight test, we were actually pretty comfortable about what the aircraft was going to do, and we knew the problem areas where we might have an issue. You've got to expect the experimental system's going to fail, and so set yourself up for the best chance of success. Now, we got so locked in on talking about the rear propulsion system. In one of our design meetings, I asked the question, well, what happens when the front engine fails? And I got a bunch of blank looks. And so we went back and sat down and went through that whole process as well. So you also have to look, is the experimental system going to be able to get you home? And what do you need to be able to make that happen? So you can get very easily locked in on that experimental system, but you do need to look at the other bits of the aircraft. And general aviation piston engines don't generally have nearly as good a record as the turbines on transport aircraft. We had some unique risks. So the powertrain limits, everything out of the powertrain in the back is set with a data file. It's a huge table of numbers. What's the maximum power setting I can command? What's the overspeed RPM limit? What are the current limits, the temperature limits? There's a huge table of these things. And so configuration control and management became very, very important. And so the team actually went through a lot of effort coming up with a software tool where they could set up the configuration that they wanted, cross-check to make sure that the file they were about to load was indeed what they really wanted. They would load it into the systems and then download the configuration from the systems and cross-check it again. So they'd ensured that what they were putting in was what they wanted, and then the systems had actually accepted what they'd put in, and we had the correct settings in the back end. So there was a huge amount of work done on that. Electrocution and arc flash. Probably not too many people here familiar with working with high voltages. You can think of an arc flash as an electrical explosion with 800 volts and thousands or tens of thousands of amps. It's essentially an electrical explosion, and that ultraviolet light that you would get like from a welding arc, that's enough to cause a 3rd-degree burn, damage your corneas, hearing damage from the explosion, all that molten shrapnel being blown around. And so they essentially have what amounts to this bomb suit, an arc flash suit that's certified to a certain level of arc flash protection. And that was required anytime we cracked open any of the 800-volt high voltage systems. So the system was designed to contain most of those, but if somebody was working on that high voltage system, they had to be in that arc flash suit to protect them. And then the other thing was we had an education campaign. That's a 210 horsepower blender on the back of the aircraft that can go like that to full power. And so we had to educate the lab about that. We had to put some maintenance safety cutouts in the aircraft so that the maintainers could be sure that that rear nacelle was not powered, that motor wasn't going to spin up, that they weren't going to electrocute themselves. And we actually had a fairly large campaign around the lab as well, just letting everybody know of the kind of unique features of the aircraft, including the batteries as well, what to do if they start seeing flames coming out of one of those side vents. Notify the fire department so that they're aware that we have high voltage lithium batteries, and we actually brought them over and they did some training on the aircraft as well and some familiarization. So a large effort to try and keep everybody safe around the aircraft. Another one, if we drag down the 28-volt electrical system and one of the computers glitches, we lose the rear propulsion system. And so on this particular aircraft, there's an electro-hydraulic pump that's used to retract the main landing gear. It's a fairly large draw. We wanted to make sure that any of these other transient conditions that we could have on the 28-volt system weren't going to cause us a problem. So we actually jacked the aircraft up, did gear swings with the rear propulsion system powered. So we were one throttle lever movement away from spinning the rear propeller. And so we'd gone through a lot of additional mitigations to make sure that if that propeller lever did get bumped, that we weren't going to blow the aircraft off the jacks or hurt somebody. And we actually loaded the aircraft up with maximum electrical loads, the battery down at about 50% capacity, cycled the gear multiple times and made sure that that system was going to be able to handle those kind of transients and brownouts. One of the things that really helped us on this was the new shipset battery. So we opted for quite an expensive battery. It's a lithium shipset 28 volt, but it's able to provide high currents for starting. And it's actually got a lot of capacity in it for the size. So that after doing all those tests, we were very comfortable that the system was going to do what we wanted it to do when we needed it to do it. What have we done to date? We did like I said, the initial baseline testing to grab some initial data to validate our model. Fit in system analysis where in light envelope we have a problem. We did some acoustic fly paths. How much noise does this thing generate with the two piston engines? And then we just last Friday went and flew it over again with the in this hybrid configuration and got the noise with the rear electric propulsion system to compare the differences. I talked about doing an extensive amount of ground testing, both low and high speed taxi, and how well the aircraft accelerated down the runway. We took that data back into the models, where the models predicting what we were actually seeing, and they were actually. So we felt very comfortable going into the first flight that the aircraft was going to do what we wanted it to do. We've done 8 flights now, updated as of Friday. Again, the modeling was accurate. Most of what we've gathered has been safety-related flight test data. How does the aircraft climb on one engine? The front engine's out, the rear engine, the windmilling of the rear propeller. It takes the propeller 90 seconds to feather on the rear. It takes an incredibly long time. The front one will feather in about 3 seconds. The rear one takes 90 and has to be manually held. So can we climb away with the rear propeller windmilling as opposed to feathered? How does it perform engine out? We actually did a simulated profile in with no engines to make sure that I could get the aircraft safely back on the deck. So working through a lot of those kind of considerations for the safety side. The next step we're rolling into now is a little more operationally representative missions, cross countries, climbs to higher altitudes. And we've expanded out the flight permit and be looking to expand it some more. The first flight was just 5 minutes up and around the pattern. The entire goal of the first flight is a successful first landing. And so we went up and we're actually able to prove that. And then after that, we started expanding it out. So the first flight was fairly short. We've been up to 48 minutes now. We had some near misses and some gotchas. The windmilling motor, this was one that we had planned as a test. We didn't think we could do it in the test cell, but the test cell guys were pretty keen and actually were able to stumble across an issue with a throttle chop. So what happened with the throttle chop was the dyno has enough inertia to spin down the motor. The motor generated about 2 amps, and that 2 amps was seen as a charging current by the system. The batteries were too hot to charge, so it disconnected the system, shut down the whole propulsion system, the back end. And this we could have very easily got in flight just by pulling the throttle back to idle and having the rear propeller windmilling. And so we actually went through and changed some of those configuration files and made sure we wouldn't hit that. The other advantage we've got obviously is the front motor as well. We do have a procedure if we do shut the system down, we're able to feather the rear propeller, get it stopped, get rid of that voltage, and then restart the whole system successfully. The coolant pumps. Even simple items are getting smart. So these are two 12-volt coolant pumps, circulate glycol. February, we're flying, the coolant gets cold, and all of a sudden we're getting pressure indications, like we have a pump failure in flight. And a pump failure is fairly serious to us. So we were getting ready to shut down the propulsion system. Looked into one of our synoptic pages on our display. No, we're still showing pressures, it's just lower. Well, it turns out the pumps are smart. I'm a coolant pump. If the coolant's at 0 degrees, why am I working so hard? And it automatically derates to 50%. We went back, talked to the manufacturer, and he said, oh yeah, I should put that in the data sheet. No idea that these pumps were actually smart, and we had this auto derate function. And so we're kind of working our way through that. We're using pressure switches to indicate that we have a system fault. And of course, when the pump derated, the pressure dropped low enough, we started getting these lights. And then the one that kind of scared us was the propeller whirl mode. For those of you that aren't familiar, propeller whirl mode is an unstable motion in a propeller. Kind of popped up. It was identified back in the 20s and 30s, but really didn't manifest itself in flights until about the 1950s with the Lockheed Electra. And they had suffered some damage on the nacelles. The nacelle became a little more motion than the nacelle. The propeller went unstable and actually ripped the wings off a couple of Electras with a significant loss of life. It comes about from a change in the center of gravity characteristics of the motor and the propeller combination. And so going from those large heavy pistons to a long slender turboprop introduced this propeller whirl mode. Well, we've all of a sudden gone from a long slender turboprop now to a very short light electric motor. And so those conditions are different and novel and needed to be looked at. We had initially asked a question about it early on in the test program. Went and looked at the regulations, and it said that you only need to address it for part 23 if you're doing a turbine engine. We're not doing turbines, so we didn't look into it too much further until a Transport Canada engineer said, it's a novel propulsion system, I need a whirl analysis. Well, we went through, did the whirl analysis, and lo and behold, right in the speed range that we were looking to fly, that propeller could go unstable. And so thankfully we went back, stiffened up the motor mounts, and we're able to show actually on the chart here, you can see we have a safe level of margin out beyond the speed of the aircraft. But initially that lower curve intersected at about 190 mile an hour, which is within the speed range of the aircraft. So one of the big takeaways was, get the knowledge back from the legacy requirements, but also sometimes the certification agency really is there to help. So this is an amalgamation of kind of the flights. This is actually our first flight, first takeoff. Still got the unique noise. The propeller noise kind of dominates still out of the rear. We did retract the gear for the pattern around for our first landing.
We did. Alrighty. That flies nicely. Yeah.
That's us coming back in on the electric. It flies like a heavy Cessna. And in terms of engine control in the rear, it operates very much like a PT6 out of the Twin Otter. There we are revving it up with the prop noise. And with the prop back slow, there's not much noise left anymore. Very simple operation on the motor. You set the torque, you set the RPM. It's, like I said, it's very much like the PT6 on the Twin Otter. Tradition is you take the chief designer's wallet. So we had his wallet for the flight. He tried to send us up with some marshmallows to go along with the batteries, but we elected not to do that. And park the aircraft. Where are we going next? We've got some more whirl mode data to gather. So we have a set of accelerometers in the back that Patrick will probably show you. Some more hot weather testing, obviously next summer. We just did the acoustics. We've got our envelope expanded out to go to higher altitudes. The higher you go in altitude, the less insulating properties the air has. And so with these high voltage systems, there's other things that you need to look at when you get into high voltage systems. A regen recharge function. We don't have that on the aircraft now. Would it be nice to have? Yeah, possibly. There's some other technologies that we're looking at, maybe new batteries, maybe a hydrogen fuel cell. It's a test bed. It's there to try new ideas. And the last thing I'll say is it took a large team. We had a lot of different labs from all over the place. The one takeaway I will throw out for that is the labs are very, very knowledgeable in their areas, but maybe not in aviation. So they're very smart in their areas, but maybe what is normal for operations in high voltage in a building or in a surface vehicle is not always applicable. So you do need to pull in those specialists, but you do also need to know their kind of limitations and the background that they're from. Again, may not be directly applicable to aviation, but we can definitely learn from them. And it took a large team. Like I say, the battery guys, we had the structural, we had the acoustics, structural dynamics, we had the test cell, the gas turbine lab. There was a lot of people involved in this program, and we wouldn't have been able to do it without all of them helping out. And I think that is it. Are there any questions before we move to the aircraft? Yes, go ahead. You bet.
I'm gonna just interrupt the questions from the floor audience here, because you'll all have an opportunity to ask questions after the Zoom call is finished. So what I'm going to do now is just go through the questions that came through from the Zoom callers, and I'll read them out, and here will respond. I might even respond to some. First one was from Nicola, and it was about she was asking, are we using a Cascadia motion motor drive?
Yes, we are.
And the answer is yes. That is
PM150DZ.
Patrick has the exact model number if you're interested. I need to go out. Say it again.
To the mic? Is this the mic?
You can tell me.
Like is there.
It's a PM150DZ Cascadia controller.
This one's probably muted. You good? Are you off mute?
No, this one should be. This one should be.
Okay.
That one's active. Okay. So that was Nicola's question. Then we had question from Alexander about fire suppression. Were any potential methods of battery fire suppression looked into, or was the potential of thermal runaway too high to make containment the only viable option?
So it wasn't considered seriously because it's very, very difficult, if not impossible, to stop thermal runaway once it's begun. Everything required for sustainment of that fire is present. As the battery burns, it actually produces its own oxygen to sustain the fire. So suppression was not seriously considered. We elected to contain and prevent propagation to the rest of the modules.
And I'll just add, the rule of thumb for fire departments is 5,000 to 6,000 gallons of water for a car. And we've got 2 cars worth in there.
So the next question from Francois, I think was, how did you select propeller type, aluminum versus composite? Any special considerations with an electric motor besides losing the hydraulic propeller pitch control? Again, maybe Patrick, you want to take that one?
So selecting it wasn't as challenging as you might think. There are not a lot of propellers that have electric governing in them. All traditional general aviation propellers have hydraulic governing because you have a source of high pressure hydraulic fluid that is proportional to the piston engine's RPM. Once you take that away, you either have to bring back hydraulic pressure by introducing a pump, which was seen as too complex, or you select a prop that can be governed with an electric motor. And there are not many on the market. There are a few in the experimental world, and only one that was certified, and that's from MT Propellers in Germany, and that's the one we selected. And the blades themselves are interchangeable on a number of their hubs, but these propellers are certified for a Cessna 337, obviously an unmodified regular 337, but that was the selection process.
Russell asked the question, did we measure the battery pack specific energy with the final containment system? What was the weight management part of the project objectives? So I'll answer the second part of that. Weight management certainly was a part of the project objectives. Of course, we're limited by the capacity of the aircraft. We stayed within the original aircraft certified weight and balance envelope, with the exception that we exceeded the landing weight. Unlike most airplanes, an electric airplane does not lose any weight as you burn off the energy with a little bit of fuel in our case. So certainly there was a lot of effort to stay within the approved envelope of the aircraft from a weight point of view. The first part of the question on the battery
I'll
specific.
just add, somebody suggested we go on a diet too.
We didn't.
No.
So what was the first part of the question?
Battery pack specific energy with the final containment system. I presume the question is about mass specific energy.
Yeah, I'm not sure I fully understand the question, but in terms of the containment system, we verified it with the exact battery we're flying with. So it was verified with the particular cells and their specific energy and their specific power. So I'm not sure I answered your
I
question.
think maybe if you talk about how we decided to go with an automotive certified because it was available and went through certain testing
Right.
versus experimental battery to get us the best thermal energy we could, or the best overall.
Yeah, so what Pete was saying, in case you couldn't hear, was there were a number of reasons we selected the battery we did, which comes from the electric car market, is one, availability. It's very hard to buy cells directly from the manufacturers because there's such a demand for high quality cells, both from the automotive and the computer and the cell phone market. Buying onesie twosies for airplanes here and there is very challenging. So we bought directly from the automotive market. They have a long service life. They've been in cars for years. Long service history of safety, and they come from a tier 1 supplier. So as the aviation electric market matures, we'll have, I think, greater and more varied access to cells. There are a number of companies around the world who are trying to certify aviation modules, but at the time when this project was begun, which was about 3 years ago, there were very few options, and the automotive sector seemed the best choice.
So yeah, the question was mass specific energy. In other words, number of kilowatt hours per kilogram of the. So I think that's.
Yeah, so understood. So the battery we selected does not have the best energy density of all cells available. It's kind of in the upper mid range, but we selected it for all the reasons I just gave a moment ago. There were better cells back then, and there are certainly better cells now. That's the exciting thing about this sector, is the batteries are always improving, and we can already do useful missions now. So just moving forward, it's going to get better.
So the next question on batteries was about cooling. Do we have active cooling on our battery systems? I'll take this one. The answer is no. The weight penalty of incorporating sort of a liquid cooling or more active cooling system was prohibitive for us. As you heard the guys describe, basically we manage the thermal energy and the temperature limits by controlling how much power we draw from the batteries on this experimental test bed. Related to that, though, the cooling system that is on board the aircraft is required, the liquid cooling system is required to manage the temperature of the motor and the motor controller, the inverter. And so, and that's a critical system on this aircraft. We have, oh yes, the question about, it's probably been answered, was the pack derived directly from a car? Yes, is the answer. But we're not going to tell you which automotive, which car company we got that from, because they didn't want us to share that. Two cars. Yeah, two of the same kind of car.
It's not that they didn't want us to share it. It's just we're using it on an off-label use, and we don't want to make anyone uncomfortable.
So for those online, yeah, it's not that the car company was upset that we not use their name. It's just that we're using it in a way that they didn't intend, so we didn't want to make anyone uncomfortable. What is the weight of the modifications? What is the new empty weight of the aircraft? Empty weight is a funny term.
Before we get in.
The airplane's useful load in its current configuration is enough for these two guys and a bit of fuel, and that's about it. So it's as we said before, it's not a very practical airplane. It's a test bed. That being said, we're pretty confident we can get an hour of electrical endurance out of it with the carrying two guys and enough fuel to fly for an hour with some reserves. There's a final question here. I think it's to be the last one we'll take, is what are the main differences between automotive and aviation batteries other than energy density? I would say there is none from an energy density point of view. You can elaborate on this, but I think the main thing, one of the lessons we've learned throughout the entire program is that the hardware componentry, the sensors and the lack of redundancy that's acceptable in an automotive environment is not acceptable in an aerospace environment. So all of these components that are suitable for automotive applications are not suitable directly for use on aircraft. And so that's being addressed now in the market. You have companies like Magnex building components which have sufficient amount of redundancy and sensors and so on that you can handle some failure modes without having to shut down the propulsion system. In the automotive world, that is the way you do it. If something goes wrong with the system that may or may not be catastrophic, you just shut off the engine and the car comes to a coast on the side of the road, and you call CAA and get towed.
I'll just elaborate a bit. The differences are mostly in use and how you drain them. So on a fundamental chemistry level, there are very little differences. It's the same chemistry. You might select a different type. For those of you who may not know, there are two basic families of cells. There's energy cells, which are optimized to produce a large amount of energy, and then there are power cells to produce a lot of that energy very quickly, but maybe not have as much energy as an energy cell. So depending on your type of aircraft, you might select, for instance, if you're only using the electric motor to climb, you would use a power cell, and then you would use your piston motor to sustain flight because the fuel is more energy dense. Whereas if you have a pure electric airplane, you either have to have a hybrid battery pack with both energy and power cells, or select a cell that is kind of a compromise between the two for the climb power requirement and then the endurance requirement to continue the mission. So is that it?
Jeff, are you available to do a wrap for the online attendees?
Sure.
Perfect. Thanks.
Hi, greetings. Thanks everybody on behalf of the Zoom people. I'd like to thank all the NRC people and the CASI people who helped put this together. With this hybrid model was an attempt to give some very interesting access and information to people who would join CASI and benefit as members from a special tour and event, but also to make it open to a wider group who couldn't necessarily be in Ottawa or couldn't necessarily make it. So thank you very much, Malcolm, Patrick, Pete, Ray, for your time, and congratulations on a great project. My background was from the engine lab, so it's great to see how NRC provides a multidisciplinary team right from the start to do great things for Canada. And we look forward to the future work and future updates for the CASI group. So thanks again, and enjoy the rest of the evening.